Hi, I'm Joshua Turcotti, and this is going to be a webcast version of CS 170's discussion number 8. Today we're going to be focusing almost entirely on linear programs. Now, you've already seen linear programs introduced in lecture and the notes, so we're going to only spend a little bit of time going over the definition of them before moving on to some properties and applications of them to problems. First, we're going to make sure that you understand the two basic ways that we can write down a linear program. Namely, we can write them down in terms of individual variables, like x1, x2, x3, and so on, or we can write them down linear algebraically, using vectors. Both of these ways have their advantages and disadvantages, and you'll see both. The advantage of using an individual variable, a more arithmetical approach, is that it can be a lot easier to see what the actual constraints represent. It can be a lot easier to see where various minima and maxima and where various values come from. And it can be a lot easier to write down your constraints and such in the first place. An example of a linear program written in this form could just be to maximize a simple linear function, such as 2x1 plus x2 minus x3, writing down suitable constraints also in terms of these variables, such as x1 is less than or equal to 1, x2 plus x1 is less than or equal to 2, and x3 is greater than or equal to 5. Normally, we'll also be writing down positive or at least non-negative values for each of these. And this is an example of a linear program written down in terms of individual variables. Now, it's often more concise to express these linear programs in a linear algebraic way in terms of vectors. Namely, you can see that each of these constraints and the objective function kind of looks like the dot product of a constant vector and our variable vector x. For example, our constraint, or rather, our objective function, can be written as the dot product of the vector 2, 1, negative 1 with the vector x1, x2, x3. If we choose to denote the vector 2, 1, negative 1 by c, then we can also write this as maximize c transpose x, which is much more concise. Similarly, we can define each of the constraints to be a vector. For example, we can let the vector a1 equal our first constraint, so a 1 for x1, zeros for the coefficients of x2 and x3. Similarly, we can let a2 represent the second constraint, having a coefficient of 1 for x1, 1 for x2, and 0 for x3. And we can let a3 represent the third constraint, with coefficients of 0 for x1 and x2, and a coefficient of 1 for x3. By combining these vectors as the rows of a matrix A, defined to have a1 as its first row, a2 as its second row, and a3 as its third row, we can express all three constraints together just by saying a times x. We can note now that ax is just going to be equal to a1 transpose x, a2 transpose x, a3 transpose x is less than or equal to a vector representing the constant values in our constraints, 1, 2, 5, which we'll define as another vector b. Now, you can see we ran into a slight problem here. If you take a look at my math, maybe it'll become clear in a second. But basically, the problem is that in our arithmetical phrasing of the linear program, we had x3 is greater than or equal to x5. But when we're doing this comparison of vectors, we have to do a component-wise comparison, which means that when we compare two vectors in R3, we just check, is the first guy less than or equal to the first guy, first component less than or equal to first component, second component less than or equal to second component, and third component less than or equal to the third component. There's no notation for saying 0th and first components are less than or equal to their counterparts, but the last component is greater than or equal to its counterpart. There's no weird notation for that. So what we have to do sometimes in order to be able to express these linear programs in linear algebraic form is to play with the numbers just a little bit. For example, we'll note that we can take this third constraint right here, and we can transform it by multiplying both sides by -1 into an equivalent constraint. Negative x3 is less than or equal to -5. Then all we have to do in order to make our linear algebraic phrasing of this correct is simply to change the 1 in A3 to a -1 and the 5 in B to a -5. And then with these definitions of A, B, and C, we can concisely express our linear program written out originally arithmetically as simply max C transpose X subject to AX is less than or equal to B. And then we'll also throw in X is greater than or equal to 0, where X is now a vector. This is a much more concise expression of linear program, and you'll see it matches up with the expression that's given up here. We often use this because it's easier to look at theorems involving duality and optimization in terms of matrices and vectors as opposed to just large numbers of coefficients. Now, as you saw just now, as beneficial as it can be in terms of concision to write linear programs in terms of matrices and vectors, there are often small details in the formulation, such as our x3 is greater than or equal to 5, that make it difficult to do so immediately. That brings us to the first problem on this discussion worksheet, involving performing various transformations in order to get arithmetical linear programs into linear algebraic linear programs. So let's take a look. Here, I actually wrote down that we were looking at a maximization. But what if we wanted to write it as a minimization instead? Right? So we can define our standard form as above to only encompass those linear programs which are minimizing an objective function. So what do we do if our objective function is a maximization here? What do we do? It'll involve a transformation of the vector C. Let's say that as above, we're trying to maximize C transpose X. Let's even write out some specific values. We'll work with only two variables now. We'll just say that this is equal to x1 plus 2x2. How do we write this as a minimization? Well, we can just do a change of variables, where we define C hat to be equal to -C. Because, as you know with inequalities, if A is less than or equal to B, the -A is greater than or equal to -B. Flipping sign also flips the direction of inequalities. How can we apply this? Well, now the max of C transpose X for suitable X, we'll use the fancy word feasible for suitable, is going to be exactly equal to the minimum of C hat X for all other feasible X. So this transformation allows us to seamlessly switch between a maximization problem and a minimization problem only by changing our C vector that represents our objective function. Since the only constraint in formulating linear algebraic linear programs is that just C is a real vector, it's perfectly legal for it to have negative entries. Now, we can also take a look at the case of having constraints that are, in a sense, pointing in the wrong direction. So let's say that we're given, to begin with, a minimization as we want, minimize C transpose X, but when we're defining our feasible set of X, we're given AX is less than or equal to B, as opposed to the AX is greater than or equal to B that we want to have in our standard form. How do we transform this? In an extremely similar fashion. We can just multiply all the entries of our matrix A by -1 and all the entries of our vector B by -1 to obtain A hat equals -A and B hat equals -B. Then we can state that AX is less than or equal to B if and only if A hat X is greater than or equal to B hat. And so we can rewrite our linear program as minimize C transpose X such that A hat X is greater than or equal to B hat. And will once again be exactly in the standard form that we're looking for. So now we can consider another small hijink that can come up. What if it's possible to have negative decision variables, as these x's are sometimes called? What can we do here? Well, we can simply look at the negative of x instead. And if we're careful, we can actually rewrite our linear program with our negative x's. So I'll write out the transformation we're going to be looking for here, where our problem initially is going to be that we have a linear program of the form minimize C transpose X such that AX is greater than or equal to B, but X is less than or equal to 0. Well, we can show that this is equivalent to minimizing C hat transpose X hat, where C hat is the negative version of C, as above, just like X is the negative version of X hat, such that A hat, X hat, and we don't have to flip the sign here, is greater than or equal to B hat. Or it's not even necessary to invert B right there, because the negatives in the x's and the negatives in the a's will cancel out. So the constraint A hat X hat is greater than or equal to B is perfectly equivalent to the constraint AX is greater than or equal to B, but now we have X hat is greater than or equal to 0. And this is once again a linear program in perfectly standard form. The very last transformation that we'll consider is when it's not only the case that x is less than or equal to 0, or that x is greater than or equal to 0, but it could be either one. We have decision variables that could be any real number. And this is a perfectly feasible, and this is a perfectly reasonable thing to assume we could encounter in the wild when we're looking at linear programs. A valid interpretation could be that each of the decision variables just represents a point along the real line, for example. And maybe what we're trying to do is just optimize some sort of distances between points on a real line, some weird linear combination of their sums. And it only makes sense to consider this problem when our points, x1 or xi, x2, x3, x4, these points are allowed to be anywhere on the real line. And we have a different problem if we only look at points along the positive line. If we want to look at this problem, how do we do it? How do we write out a linear program in which the decision variables can be either positive or negative? Well, the answer is to double the number of decision variables. Can you think of how we can do that to transform this problem? Well, consider x1 in R. It's always the case that there exist two other variables, which we'll call x1 plus and x1 minus, both positive, such that x1 equals x1 plus minus x1 negative. In fact, for most values of x1, there are an infinite number of such pairs, but what matters is that there always exists at least one. So, if x1 is equal to 5, then we can simply choose x1 positive equals 5 and x1 negative equals 0. And then we'll still obtain the desired value for x1. If you have that x1 equals negative 5, then we'll just flip it. We could set x1 positive equal to 0 and x1 negative equals to 5. So, looking now at a linear program, if we have minimize C transpose x subject to ax is greater than or equal to b for unconstrained x, what we can do now is just minimize C transpose x plus minus x negative, where these are just the vectors whose each component is the positive component of x and the negative component of x, such that a x positive minus x negative is greater than or equal to b. For x plus is greater than or equal to 0, and x minus is greater than or equal to 0. Now, at first, it appears that these are not, in fact, in standard notation. And they're not quite in standard notation yet. We have to transform C and A a little bit, but there's an easy way to do this. Let's just say C hat equals C with negative C, just like that. And then, if the original C was an element of Rd, this will be an element of R2d. But if we just take C hat transpose times x plus x minus, dot product right here, this is going to be equal to C transpose, to just C transpose, not C hat transpose, to C transpose x plus minus C transpose x minus, which equals what we desired above. Similarly, we'll define an A hat to be equal to A over negative A. Or, I'm going to do a slightly different thing here. We're going to define A hat to be equal to A with a copy of negative A adjoined to the right of it. And if A was an element of R, let's say, K by D, then A hat is going to be an element of R, K by 2D. And further, if we just do A hat times our vector x plus x minus, then this is going to be equal to ax plus minus ax minus. So now our linear program, and we'll quickly just denote this x plus with x minus adjoined below it as x hat. Now our linear program up here can be rewritten minimize C hat transpose x hat subject to A hat x hat is greater than or equal to b, and x hat is greater than or equal to 0, which once again is perfectly standard form. Now, I hope these examples gave you a good sense for how you can convert seemingly non-standard form linear algebraic linear programs into standard form ones via changes of variables. You may encounter sort of similar problems in which you're given slight variations to it, like maybe even an x squared appears. Maybe you're looking at an objective function. If I can find a good place to write, we'll grab this little box. Maybe if we have an objective function that's minimize x squared plus 5y, such that y is greater than or equal to 3 and x is unconstrained, then we can simply just define x squared to be equal to a different x hat here, where this x hat is strictly positive, and then rewrite this linear program as minimize x hat plus 5y, such that y is greater than or equal to 3, and x hat is greater than or equal to 0. And this is in standard form, even though you see a nasty squared term in the original. I just give you this example to show that there are a lot of linear programs that can be transformed relatively easily into standard form. Now, let's move on to a problem. Let's skip duality for now. Duality is sort of the second half of our discussion of linear programs, and we'll come back to it in later problems. Let's skip it for now. Let's move on to a problem in which we're given a situation and we want to try and formulate an LP that represents and will give us the answer to that situation. So here we have I different workers, and each one of them can choose to spend their time. So we'll go x1, x2, all the way through xi are I different workers. And each one of them chooses to divide their time among j different jobs that have to be completed. So for example, if there are 2 jobs, maybe the first person chooses to spend half their time on the first job and half their time on the second job. And the second person chooses to spend none of their time on the first job and all of their time on the second job. The constraints here are that every single worker can spend no more than a total of 1 day, where these numbers are represented in units of days, working, so it could not be the case that x3 right here spends 3/4 of a day on job 1 and 3/4 of a day on job 2. This is a situation in which we do not allow overtime. And we have to have the constraint that no individual job can be worked on past completion. So here, what I actually wrote down was that x1 okay, yeah, I wanted to make sure I got the phrasing of this question correct. This is actually an illegal situation right here, because here we have x1 spending half a day on a job, and x2 spending an entire day on a job, which adds up to 1.5 days worked on a single job. We're actually going to have the constraint that the total number of days spent working on any individual job by all workers has to be less than or equal to 1. So let's even refine our notation a little bit here and say if the worker xi works on job j, then we'll denote the time worker I spent working on job j by x sub ij. And we can start to sort of write out constraints for these in a second, but for now we can basically see that to formulate what's going on in this problem, all that we have to look at is the time that each worker spends working on each job, this x sub ij, which is just going to end up giving us a matrix in space R ij. And this matrix is going to encompass all of our decision variables. What we note is we still haven't considered our actual objective function. We'll do that in the parts below. But we have totally come up with our decision variables. The first part of looking at an LP problem is always to come up with the decision variables. What do you have control over? We don't have control over the number of jobs. We don't have control over the number of people. Or, as we can see, we also have these sort of payoffs. All we have control over is how much time each worker spends working on each job, given the constraints. So let's write out the constraints too. Well, what are the types of constraints? We have a hint that there are 3. Can you think of any of them? Well, constraint number 1 is going to be the first thing we mentioned, that each worker, so for each worker, the sum of the time that they spent working on all of the different jobs, so for each worker, the sum of the time they spent on each job is going to be less than or equal to 1. They cannot work for more than 1 day. No overtime. That's one constraint. What's the second constraint we mentioned? Well, the second constraint is just going to be that every job cannot be worked on for more than a single day. So for all jobs, the sum over all workers of the time spent working on that job by that worker also has to be less than or equal to 1. Finally, we want to have these decision variables make some sense. So there's going to be no such thing as negative time. These are all going to be strictly positive amounts of time that each worker spends working. And we can see that these 3 constraints are mathematical interpretations of the verbal rules that we discussed above. And any matrix X whose entries satisfy these 3 conditions is going to give you a valid plan for allocating time to different workers. That satisfies the obvious constraints that we're looking at. So we've successfully defined our feasible set of X's. Now we have to have a way to choose which element of that feasible set is the best way to allocate time to all of our workers. In other words, we have to outline our objective function or our maximization function. Let's look back at the problem to determine exactly what that maximization function is. And namely, we see that there's another matrix we're considering, A. And the matrix A assigns a value to the work that each person does on each job. So the example that we're given is that if x sub ij equals c for some constant c, then the value contributed by that person's work is a sub ij times c. So a is really just a little scalar value that tells us how much it's worth for a given worker to work on a given job. How do we turn this into a maximization function? Well, we can consider both a and x to be vectors because we note that they both have the exact same dimension. They're both an element of Rj. And we can just take the component-wise product, or the dot product, of these 2 matrices interpreted as vectors, which is really just the sum over all ij of a sub ij, x sub ij. And this is actually going to be our objective function. So we now have enough information to write out our linear program for this problem in its entirety. What we're going to try and do is maximize the sum over all ij of a sub ij, x sub ij, such that every single worker spends no more than a single day working, and every single job has no more over all workers than a single day's work put into it, and that these are all positive values. We can write this linear algebraically if we want a more concise form as just maximize AX, or A is a matrix right here, maximize AX such that A times the vector consisting of all ones is less than or equal to 1, and the vector consisting of all ones transpose times A is less than or equal, this is also going to be a vector, is less than or equal to this, and X is greater than or equal to 0. And this is the formulation of our linear program. Oh, these are supposed to be X's, not A's. And this is the LP corresponding to this situation. This was an example of taking a word problem and turning it into a linear program. We can now, after formulating this, just plug this in to any of the many efficient linear program solvers that are available, and we'll get the optimal assignment of workers to jobs that maximizes our objective function. As you can see, it's really a quite powerful technique. Now, we'll also walk through applying it to another well-known problem, which is linear regression. The problem input doesn't explain it all that well, because this seems you already have some familiarity with it, but basically linear regression is when you're given a bunch of sample points and told to find a line that best approximates these sample points, which is sort of equivalent to minimizing distances of some sort from points to the line. This is a very, very useful problem in statistics because it allows us to give a very compact model for a possibly chaotic and all over the place data set. What we're doing is basically assuming that the one coordinate for these points is just going to be in Rd, or rather Rn, and the other is just R. So each of these points sort of has two coordinates. It has an input component, we'll call it AI, and it has an output component, BI. And our goal is to choose a vector X such that the BI can be accurately predicted just by dotting AI with X. This represents a line, and we want this to be a good approximation for BI. There are various ways that we can measure how good an approximation it is, using various different norms, and the one that we'll be using here is the L1 norm, which for a vector is just equal to the sum of the absolute values of the entries for it. I should phrase this a little bit differently, which is that AI.x and BI are actually both going to be real numbers. So this quantity right here, AI.x minus BI, is just going to be a real number representing in some way or another the distance between our prediction for a point and its actual value. And since we're given a large number of these points, specifically we're given n of these points, which means this should be an RD, we're given n of these points, we actually have n of these errors. We have a1x minus b1, we have a2x minus b2, all the way to anx minus bn. And we want to find a way to come up with a cost function that actually tries to minimize all of these errors. Since this is a vector, which we know can also be expressed as a matrix A, where A is just simply defined to have rows consisting of the sample points times X minus b, where b is a vector whose components are the labels for those sample points, we can see that our total errors from trying to predict the sample points A using the vector x is going to be all the components of this vector. Since we can only perform optimization, now obviously we want to optimize because we want to drive this vector as close to 0 as possible. Since we want to perform an optimization, we have to actually choose a norm for this vector. For this problem, we're going to be choosing the L1 norm, which is just basically going to be equal to the sum of the absolute values over all I. So this is sort of an outline of what linear regression is, and now we're going to try and formulate it as an LP. We've already gone over what our cost function is, but we can see that if we just write out what we have so far, it's not actually going to look like a linear program. A and B are fixed, so we'll assume that x is our decision variables, and we're just going to copy this. We're going to try and minimize over x the sum of the absolute values of a sub I x minus bi. And as you can see, this is actually the entirety of the linear program. There are no constraints that we're going to be put on x, because any possible line is a possible predictor for this data. The only problem is that this is not a linear function. This does not satisfy our golden standard form. So how do we change this? How can we go about a sort of change or an addition of variables like we did above in order to turn this into an LP? Think about it for a second, and if you can't think of anything, then proceed to watch. What we're going to do is define what are called slack variables. We're going to take t sub i's, one for each n, and we're going to just want to have the fact that t sub I is greater than or equal to the absolute value of a sub I x minus b sub I, because then our objective function becomes something linear. Our objective function just becomes the sum of the t sub i's, which we can also express as our one vector dotted with t, right? So now we've obtained a linear objective function. We've introduced a problem, which is now these constraints aren't linear. But there's a very easy way to turn this constraint into a linear constraint. How do we go about doing that? Well, we'll replace this one constraint with two. Namely, we'll have that each ti has to be greater than or equal to both a sub I x minus bi and the negative of this, b sub I minus a sub I x, because we can see that these two are actually equivalent to each other. For two real numbers, a is greater than or equal to the absolute value of b if and only if a is greater than or equal to b and a is greater than or equal to negative b. And this is just a little fact of logic that you can verify. So now that we've performed this transformation, we can take a look and see that we have our linear objective function and we have our linear constraints, which gives us a linear program whose output will be a value of x, because we're minimizing over x, that gives us very low costs as measured by this L1 norm of predicting these data points with this line. This is an extremely powerful technique that we can solve using our efficient linear program solvers. There's one more part to this discussion question, which is to sort of show that efficiency for solving regression follows from efficiency for solving linear programs by bounding the exact time in terms of n and d. Well, remember that things such as the interior point method or the ellipsoidal method, whose details do not matter as much as the fact that their runtime is polynomial in the number of decision variables and the number of constraints. Well, what are the number of decision variables and the number of constraints? The number of decision variables is just going to be equal to the components of x. X is an element of Rd, so we have d components of x, plus all of our t's. And we have n different t's. So we have d plus n decision variables. What about the number of constraints? Well, we saw that for each t sub I, we had two constraints, one for the positive half and one for the negative half, which gives us 2n constraints on the t sub I in order to get that t sub I is less than all the t sub i's are greater than or equal to the absolute values of these differences. We also have to throw in positivity constraints on the x's. So we'll throw in right here another, well, we don't have to throw this, maybe we do only have, I'm trying to think, do we need positivity constraints at any point in here? I think actually we don't have to write positivity constraints, because if t sub I were negative, then it would be guaranteed to fail either this or this. So if we were to be super explicit about what we were doing, we could throw in another n constraints such that each component of t is positive, but we can actually go without it. And either way, we're going to have time poly in d plus n and 2n, which is polynomial in d and n, which tells us that we can solve linear regression with the L1 norm in time that's polynomial in d plus n. So we're good. There's another variant of this we can consider, which is just with a different norm. This is going to be the L infinity norm, where the L infinity norm of a vector, let's say a vector x, I'll call it the L1 norm, is just the sum of the components. The L infinity norm is going to be equal to the maximum of all the absolute values. The difference between, so this is going to change our objective function. What we're going to be trying to do is to minimize instead the maximum over all I of the absolute value of aix minus bi. And what this corresponds to is looking again in our linear regression picture. Instead of minimizing the sum of all of these errors, this error plus all the other ones, we're just going to minimize the largest of all of these, which also has the effect asymptotically of driving the loss vector to 0, but we can accomplish it in a slightly different way. Now, as we had the same problem as we had above, which is that initially this is very much not a linear program. How do we turn this into a linear program? Well, it's actually in the end going to be even easier to turn into a linear program than the one above. Do you see how? Well, let's think it over. We still need to somehow get the absolute value of a sub ix minus b sub I. So we're still going to want constraints of the form t sub I, we're going to introduce the slack variables again, are greater than or equal to both a sub ix minus bi and b sub ix minus ai. This is going to, remember, have the effect of saying t sub I is greater than or equal to the absolute value of a sub ix minus bi. But how do we get the maximum of all these ti? Well, here's a little trick. If we're just looking for the maximum of, let's even say just A, B, and C, what we can do is we can minimize a third variable, D, with the constraints that D is greater than or equal to A, D is greater than or equal to B, and D is greater than or equal to C. Sort of, if you think of this height as being equal to A, this height as being equal to B, and this height as being equal to C, what this corresponds to is trying to choose a D that we're minimizing, so we're pushing this D down as far as possible, but it has to stay above both A, B, and C. So we're going to push this D down as much as we can, but it has to stop once it reaches the biggest of these three, right? So once it reaches the highest height right here, once it reaches B, we cannot minimize D any further. So the minimum of D subject to these constraints is just going to be the maximum of A, B, and C. This is another very useful change of variables technique. How do we implement this above? Well, very simply. Instead of so let's even just choose a global T, right? And so once we define each of our TIs to be bigger than or equal to be greater than or equal to the absolute value of AIX minus BI, we're also going to have a global T that's greater than or equal to all of the other T sub i's. And then our objective function, once we have these constraints, is just going to be minimize T. Very simple. And we can even see that this constraint combined with these constraints is just equal to the simpler constraint. Our big T itself is greater than or equal to A sub ix minus bi and bi minus A sub ix for all I. And what this is going to enforce is that T, after minimization, is just equal to the max of the absolute values of the differences of AIX minus BI for all I. And this is actually going to be our formalization of the L infinity LP, the L infinity linear regression problem. We want to similarly show that this can be solved in polynomial time, so we'll count up our variables. We still have the D components of X, and now we just have one more decision variable, our T. I'll write this over here. This is going to be our number of decision variables. Our number of constraints is just going to be 2 for every single possible value of I. There are n values, so we're going to have 2 n constraints, just like we did above. For total runtime of poly ND, just as desired. So we can see that whether or not we choose the L1 norm or the L infinity norm, we still end up with a polynomial time algorithm for solving linear regression. Just to summarize the 2 change of variable techniques that we used right here, we learned that if we want to minimize the L1 norm of a vector, it suffices to just minimize the sum of slack variables ti, where each ti has to be greater than or equal to xi and negative xi. If we want to minimize the L infinity norm of a vector, it suffices to minimize a single t such that that single t is greater than or equal to the positive and negative value of each component. And these are 2 very useful LP transformation techniques that you should take note of. Now, we're going to move on to taking a look at duality. So what is duality? The basic idea of duality is that every LP has a corresponding dual LP that gives you bounds on the solutions of the original LP. You saw this in lecture introduced arithmetically, so what I'm going to walk through is a linear algebraic way to arrive at the formulation of the dual. Let's take a look. let's write out our original primal problem. We're going to be minimizing C transpose X such that AX is less than or equal to, I believe we're looking at. No, such that AX, so I think there might actually be, we'll get to it in a second, such that AX is less than or equal to B. And X is greater than or equal to 0. This is our original problem. Well, what can we do here? Let's introduce another variable, y. And let's take our constraint on feasible X and introduce a y transpose as a dot with both sides, such that we know that I'll describe this as for all feasible X, which are all X that satisfy these constraints. For all feasible X, it is the case that y transpose AX is greater than or equal to y transpose B. Basically, we're introducing another set of decision variables. We're introducing a way to get a bunch of different bounds. For example, I could set y just equal to a vector with 1 in the first component and 0 in every component afterwards. And this would just tell us that the first row of A, dotted with X, is greater than or equal to the first component of B. It's just a way of specializing this constraint to give us a different brand of information. We can take the very, very general, very, very large multivariate constraint, matrix AX is greater than or equal to B, and choose a specific value of y that perturbs this constraint a little bit to give us a different constraint. That's still going to be true. So these are still all going to hold. But I'm not actually going to consider just any y. I'm going to make the decision that I want to consider only those y such that y transpose is greater than or equal to C transpose X. Or just even, let's say that we'll consider y such that y transpose A is greater than or equal to C transpose. And this is perfectly reasonable to do. We wrote above that we could pick any y whatsoever in Rm, where we're basically just defining A to be a matrix in Rn by M, and X is an element of Rn. We're going from saying y can be any element of Rm to saying that y is only going to exist in a certain linear subspace of Rm. What does this give us? Why do we want to look at only these specific y? Because now, if we define these to be our feasible y, now we can say that for all feasible x and feasible y, it is the case that C transpose X is less than or equal to, so I know C transpose is less than or equal to Y transpose A, and I can just throw my X on there too, because if every component of a vector is less than or equal to every component of a different vector, then necessarily the dot products with the first component will be less than the dot products with the second component. And I can plug in what I learned up here, that this is so I think I'm actually going to switch a direction here. I'm going to actually ask that Y transpose A be less than or equal to C transpose here. And then this is greater than or equal to Y transpose B. Right? So I have this expression right here. And now, what I can see is I can pull out just the first term and the last term to get that C transpose X is greater than or equal to Y transpose B for all feasible X and Y. Specifically, this tells me that now I can look at all y transpose b such that this constraint up here holds, such that, and we'll take transposes to make things more readable, A transpose y is less than or equal to C. And similarly, I only want to look at positive values of y, because otherwise, when I multiplied by y in this right here, it would flip the sign, so I need to have that y is positive in order for this to hold. Then, for all y that satisfy these two conditions, y transpose b is going to be less than or equal to c transpose x for all feasible x. If I maximize this now, this tells me that the maximum over all y of this y transpose b, subject to these constraints, is going to be a lower bound on how small c transpose x can get for any feasible x. And this is the super key point. When I perform this maximization over y right here, I'll get a value of y transpose b that is a lower bound for any feasible value of c transpose x, because this inequality holds for all feasible x and y. And this system right here is called the dual, as I assume you've seen introduced in lecture and the notes. Though this is a linear algebraic way of working towards the dual. This is useful because it allows us to verify optimality. Specifically, if I find a value of y, let's say I'm considering a value of x, right? Let's say I make the claim that x hat is optimal. This is my claim. This is just a claim. There's no way of proving this until I consider the dual. What if I find a y hat such that y transpose b is equal to c transpose times this x hat? What does this mean? Well, we know that for all feasible x, c transpose x is greater than y transpose b. So I can use my specific y hat up here that I found. This is true for all y, so I can choose my specific y hat. And I can plug this in up here to see now that for all feasible x, c transpose x is greater than or equal to c transpose x hat, which actually verifies that x hat is as small as c transpose x can possibly get. It verifies the claim. And in general, in order to perform this verification, in order to find this y, all we really want to do is look for the maximal y transpose b, because this gives us the best chance of actually being equal to c transpose x. This is an extremely useful feature of the dual, which we'll be able to apply in problems such as number 4. So let's work through what I just gave you above. Let's express this LP in standard linear algebraic form. Let's take the dual, and then let's use that as a certificate of optimality. How do I write this in linear algebraic form? Well, let's start with our vector x. X hat is x1, x2, x3, just like that. What's going to be our objective function? Our objective function is going to consist of the vector c with a coefficient of 1 for x1, 0 for x2, and -2 for x3, such that our objective function can be written c transpose x. What are our constraints going to be? Well, let's look at our first constraint. Our first constraint is going to be that x1, so we'll put a 1 for x1, minus 1 for minus x2, and 0 for x3, remember we're going to be multiplying this by x, is less than or equal to 1. Our second constraint is going to be that no coefficient of x1 here. So we have 2x2 minus x3, we're going to dot this with x, is now less than or equal to 1 as well. And finally, we're going to put that x itself is greater than or equal to 0. So, defining A to be this 2 by 3 matrix, and C to be this R3 vector, we can express this linear program up here simply as just maximize C transpose X subject to AX is less than or equal to B, and X is greater than or equal to 0. Looking back above at what we just derived, we can see that this matches up with this form of the primal. So let's remind ourselves of the form of the dual right here, and we'll write down the dual now. If this is the primal, then the dual is just going to be equal to B transpose Y. Remember how when we were working RNM, X was in Rn and then Y was in Rm. So we're going to be looking at Y, and we're going to be changing this maximization to now a minimization of Y in R3, or rather, I guess we'll be looking at R2 now, because X is in R3, and so Y is going to be in R2. We're going to be minimizing B transpose Y such that A transpose Y is greater than or equal to C. Yeah. And we'll throw in Y is greater than or equal to 0. And this is going to be our dual. Let's actually expand this out a little bit because this is not very informative. As we mentioned earlier, the linear algebraic form is very useful for plugging into theorems, but we can't always just read it and see the coefficients and know what's going on. So let's expand. B transpose Y is just going to be equal to Y1 plus Y2, because as we recall, B is this vector right here. So we're going to be minimizing over Y1, Y2, Y1 plus Y2, subject to, so we're going to take the transpose of A, which is 1, 0, negative 1, 2, 0, negative 1, and we're going to be multiplying the vector Y by this, so we're going to have 1 times Y1, so we have 1 times Y1 plus 0 times Y2, so this is just going to be Y1, is greater than or equal to C1, which is 1. C is 1, 0, negative 2. So we'll have Y1 is greater than or equal to 1. We'll have Y1, so negative Y1 plus 2Y2. This is negative Y1 plus 2Y2 is greater than or equal to 0. And we'll have 0Y1 minus Y2 is greater than or equal to negative 2. And maybe we can tidy this up a little bit if we want. This will be the minimization of Y1 plus Y2 of such that, rather, this is our feasible set of Y, such that Y1 is greater than or equal to Y, 2Y2 minus Y1 is greater than or equal to 0, or even let's just write this 2Y2 is greater than or equal to Y1, and Y2 is less than or equal to 2. All right, and this is our dual problem. How are we going to use this dual problem? Well, we're going to use it exactly the way above that we justified the existence of the dual. we're going to consider a possible x hat equals 3/2, 1/2, 0. And we want to show that this x hat is optimal for the primal. Or in other words, that for all feasible x, C transpose x is greater than or equal to C transpose x hat. We'll do this by showing that C transpose x hat is equal to B transpose y for some specific y hat. How are we going to find this y hat? Well, we're going to look for the biggest one possible, because that gives us the best chance of pushing it all the way up to being equal to C transpose x hat. How do we find the biggest possible value? Well, let's take a look. Well, we won't do this formally because we can probably just do it by inspection, by looking at this dual system up here. We want to, we're looking at a maximum here. The directions of these can be a little bit confusing. We're trying to maximize in our primal, so x hat is going to be the value of x such that C transpose x hat is bigger than C transpose x for all other x. And similarly, then y hat is going to be the minimum of B transpose y. How do we find this? Well, let's take a look at our objective function in the dual, and let's try and make this as small as possible. Let's do this greedily almost. So we know that y1 has to be greater than or equal to 1, so let's just set y hat 1 is equal to 1. Now, how small can we make y2? Well, we can see that y2 has to be at least half of y1. So we'll say that y2 is equal to 1/2. Now, we can see that our third constraint, y2 is less than or equal to, is satisfied by this. So this is indeed a feasible value of y that gives us an objective function, B transpose y hat equals the sum of them, 3/2. All right, so now we know that 3/2 is this upper bound right here. The 3/2 is an upper bound on all possible values of C transpose x. If we can show now that C transpose x equals B transpose y hat, which equals 3/2, then this implies that x hat is optimal. So let's check. In our objective function, C was 1, 0, -2. So let's compute C transpose x hat. 1 times this, 3/2, 0 times 1/2, and -2 times 0 equals 3/2. So this tells us that indeed C transpose x hat is going to be greater than or equal to C transpose x for all feasible x. We've just established this, which is equivalent to saying x hat is optimal. I hope you see how this thought process has allowed us to conclude that our guess for x hat actually is the optimal solution to the LP. In general, we're looking for a solution to the dual, and if we can show that that solution to the dual coincides with our suggested solution to the primal, this implies our suggested solution to the primal is optimal. We're going to work through one more example of computing a dual, and then we'll actually be done with this discussion for today. I suggest at this point, since I've already walked through it a couple times in both symbolic and concrete format, that you try and work out this dual yourself. Pause the video, work it out, and then resume and compare with what I come up with. Let's formulate it. X is equal to x1, x2. What's our objective function going to be? We're going to use the vector c equals 4, 7. Now, how are we going to formulate our constraints? Well, we need to have 1x1 plus 2x2 is less than or equal to 10. we need to have 3x1 plus 1x2 is less than or equal to 14. And we need to have 2x1 plus 3x2 is less than or equal to 11. So we'll define A to be this matrix and B to be this vector. R3 is an element of our 3 by 2. Now, the one last constraint we're going to throw in is x is greater than or equal to 0. But by using this definition of C, A, and B, we have sufficient information to now express this system right here as just the maximization of C transpose X, subject to AX is less than or equal to B, and X is greater than or equal to 0, which is the linear algebraic format that allows us to take the dual. What's the dual going to be? Using the form that we've derived above, it's going to be minimum B transpose Y, now considering Y is an element of R3, minimize B transpose Y, subject to A transpose Y is greater than or equal to C, and Y is greater than or equal to 0. Let's go ahead and plug in some concrete values. We're going to be minimizing over Y, B transpose Y, so 10Y1 plus 14Y2 plus 11Y3, subject to A transpose, which is 1, 3, 2, 2, 1, 3, times Y is greater than or equal to C. Let's multiply this matrix by Y. And so we'll get 1Y1 plus 3Y2 plus 2Y3 has to be greater than or equal to the first component of C, which is 4. Similarly, 2Y1 plus Y2 plus 3Y3 has to be greater than or equal to the second component of C, which is 7. And finally, Y1, Y2, and Y3 are all greater than or equal to 0. And this is the dual of the above LP. If we wanted to, we could similarly try and maximize this. It's harder to do it by hand, but to give an example, let's say that we thought, let's try and come up with a feasible solution to this. I can see that y equals 1, 1, 1 does not work because it violates the, so actually no, 1, 1, 1, yeah, 1, 1, 1 does not work because it violates the second constraint. So let's push it upwards just as much as we need to in order to make 1, 1, 1 work. And the smallest perturbation we could possibly make here would be to increase y3 by a third. So let's change this to y equals 1, 1, 4 thirds. And we can now see that the value of y1 plus 3y2 plus 2y3 is going to be greater than or equal to 4, and that the value of 2y1 plus y2 plus 3y3 is going to be exactly 7. And all of these are possible, so this y is a feasible solution to the dual. We can now plug this into our objective function to get 10 plus 14 plus 44 thirds, which I'm going to do a little bit of hopefully correct mental math and tell you is equal to 72 1/16 thirds. That may be wrong. Feel free to yell at me on Piazza if that's wrong. But I can take this 1/16 thirds, and now I can say that any possible solution to this system up here, right? So any value of 4x1 plus 7x2 is going to be less than or equal to 1/16 thirds. This also means that if I find an x1 and x2 such that this is exactly equal to 1/16 thirds, then I know it's optimal. So that is an example of how we could apply this dual in order to prove optimality of a solution to the primal. Duality is a conceptually confusing topic. I encourage you to think about it more, to derive the linear algebraic calculations above by hand these calculations right here. Namely, just really work through every step of this inequality right here because it's pretty key to understanding the dual. And hopefully, if you work through this, or if you just watch my derivation of it a couple times, you'll understand why the dual is such a powerful tool for proving that we found an optimal solution to a primal. Thank you for watching discussion number 8. I hope this helped out with your studying, and good luck on midterm 2. Have a great rest of your day.